In the last video, we gave you the intuition for why the ratio test works, and provided the sketch of a proof using actual numbers. Now let's write down a real proof. Suppose our series is given by a sub n, where the terms are all non-zero. We will assume that the absolute value of the ratio of successive terms approaches the number capital L, and that capital L is strictly less than 1. Now remember, in the last video, the key was to pick an epsilon small enough that big L plus epsilon was still less than 1. The simplest way to do this is just let epsilon be half the distance from L to 1, or the quantity 1 minus L over 2. Now by the definition of a limit, there's some cutoff called big N, where beyond that point, all the terms of our ratio sequence are within epsilon of L. So these ratio terms may start outside the range L minus epsilon to L plus epsilon, but for the terms past big N, we can say that the ratios are all within that range. So that tells us that the absolute value of the ratio a sub big N plus 1 to a sub big N must be less than L plus epsilon, which we know is less than 1. So the n plus first term is bound in magnitude by the absolute value of the nth term times L plus epsilon. Then we can say the same thing about the absolute value of a sub big N plus 2 over a sub big N plus 1. And this means that the big N plus second term is smaller in magnitude than the big N plus first term times L plus epsilon. So it's less than the big nth term times L plus epsilon squared, and so on. If we wanted to be super careful, we could prove by induction that this pattern holds, but I think this is pretty clear. Just like in the previous video, we will now point out that the series a sub big N plus 1, a sub big N plus 2, and so on is dominated by the geometric series, where the first term is the absolute value of a sub big N, and the common ratio is L plus epsilon, which we know is less than 1. Now that's a convergent geometric series, so our original series, beginning with the big nth term, is convergent by the comparison test. And so of course that means the entire series is convergent. And we're done with that half. Now the L greater than 1 case is much easier. Suppose the limit of the absolute value of a sub n plus 1 over a sub n equals L, which is strictly greater than 1. Again, we will pick epsilon so that it is half the distance from 1 to L. So in this case, it's the quantity L minus 1 over 2. From the definition of a limit, there is some big N where, from that point forward, the ratio of successive terms is between L minus epsilon and L plus epsilon. In the language of analysis, there exists a big N greater than 0, such that for all little n greater than or equal to big N, the absolute value of a sub n plus 1 over a sub n is between L minus epsilon and L plus epsilon. Of course, we only care about half this inequality, so we can rewrite this as, for all little n greater than or equal to big N, the absolute value of a sub n plus 1 over a sub n is greater than L minus epsilon. And by design, that is greater than 1. Then, just like before, we know that the magnitude of a sub big N plus 1 is greater than L minus epsilon times a sub big N. And since L minus epsilon is greater than 1, we know that the absolute value of a sub big N plus 1 is greater than the absolute value of a sub big N. Same for a sub big N plus 2. It must be greater than a sub big N plus 1 in magnitude, which in turn is greater in magnitude than a sub big N. It's easy to see from this that the terms of our original series keep getting larger in magnitude, so there's no way that the limit is 0. By the zero test, our series diverges. And that's it. I hope you can see the progression from intuition to proof, and maybe you'll be a little less afraid of Epsilon-Big-N proofs in the future. In the next video, we will tackle the root test, and I find that proof to be even easier. In the meantime, make sure you subscribe so that you are notified when it comes out. And giving us a thumbs up helps us make more videos like this one. See you in the next video.